Alrighty, well I will, now I bumped this stupid thing. Alright, it's fine. I'll begin with a word of prayer. Heavenly Father, we thank you for this opportunity we have just to meet together. Help us to glorify you what we do. Help us to understand a little bit more about chapter 12 as we work out some problems. Lord, in your name I pray. Amen. All right, so. Oh my goodness, excuse me. So, first problem I'll look at by request, number 9. So this is number 9 of chapter 12. And here we're asked to prove the intersection of a collection of subrings is, you guessed it, a subring. Okay, so by collection here, I'm assuming he means that you've got, R1, R2, I guess fine. S1, S2, let's say n of them, subrings of R, right? And so if I want to show that the intersection of those, right? So let S equal the intersection I equals 1 to n of S sub I want to show that this is a subring of the ring. Okay, so what would I do? What do you think? I'll start us out. So I'll begin by note 0 is an element of S sub I for all I. So therefore 0 is an element of the intersection, right? Right, so therefore S is non-empty. Then what I would do is I would let A and B be elements of S, right? Which means that what's that mean? It means that they're an element of every single subring which is forming the collection, right? And then we use what? The subring test, right? So 1, A, B is an element of S sub I for all I equals 1 to n, since what? Since S sub I is subring, right? For each I. And 2, A minus B, right, is an element of Si for all, or for each, if you like, as Si is a subring, right? So what does number 1 imply? Right, it says that AB is an element of S as well, right? By the definition of intersection. If it's in every single thing forming the intersection, then by set theory, AB is an element of S. And likewise, like you said, I mean, you'd say that the second one shows that the intersection ring is closed under subtraction, right? Because what we've shown is that the difference A and B, A minus B, is in each of the subrings that forms the intersection. Consequently, it's in the intersection of the totality of the subrings. So you put these together, and we got thus S is subring by subring test. And there it is. So that's number 9. I'm gonna, let's see here. Oh, let me get my cheat sheet. My cheat sheet is to remind me not to work your problems. You know, I get a list of problems and I delete them and add them. And sometimes in the process of that deletion and addition, I forget what I left. Yeah. Like, anyway, so let's see, one nice one here. Number 4 is kind of nice. I'm going to take a break from Blaine's problems for a second here. So he says, show by example for fixed non-zero elements A and B in a ring, the equation AX equals to B can have more than one solution. So for, you know, fix the choice of A and B. So can you think of an example where that would be the case? Here, how about, right, Zn. Let's think about R equals to, let's make it specific. Let's look at Z12, right? And let's look at something like 2x equals to 4 or something, right? What are solutions to that? Well, one solution to it, right? You can figure out x equals to 2, right? That's kind of the usual solution. Anything else? X equals 8, does that work? 16, 8 times 2 is 16, which is equal to 4. Yeah, very good. X equal to 8. Anything else? Let's see here. 5 doesn't work. Let's see. 3 doesn't work. 4 doesn't work. 5 is no. 6. No. 7. No. Just 8. About 9. 10. What about 10? What about 10? 2 times 10 is 20. Which is 8. Oh, that's no good.
14 works.
Oh, but 14 is just 2 again. But yeah.
Sure. Yeah.
So yeah, but anyway, but already we have, you know, that's it, right? So there's an equation in a ring, and as you can see, the solution's not unique. In contrast, if we're solving AX equals to B for fixed A and B in a group, right? In a group, in contrast, this implies what? A inverse, right? AX equals to A inverse B. So therefore, X is equal to A inverse B. So that's, you know, that's a pretty significant difference. In a group, this kind of equation has to have one solution, whereas in a ring, it doesn't have to. Anyway, I thought that was an interesting problem. All right, so
in rings, you're allowed to do that sort of thing where you multiply on the left by A inverse.
well, I was supposing that we had an inverse. I mean,
oh, if you have an inverse, can you do that sort of thing?
sometimes we have inverses, yeah. If you have an inverse, yeah. I mean, I can't do that here because 2 doesn't have an inverse, right?
Right.
The group of units in Z12 is, well, it's U12, right? 1, 5, 7, 11, yeah. So, okay, so let's see here if there's any other. Let me go on to his next problem, which was number, he wanted us to look at number. Of course, the, show the arbitrary intersection of subobjects as a subobjects problem is also interesting for groups, right? The arbitrary intersection of subgroups is a subgroup. That's another kind of basic problem that's fun to look at.
That reminds me of something in real, but I can't remember why.
That I wouldn't know.
Arbitrary intersections of
Yeah. They're
open and closed intervals.
what? Oh man, come on. Yeah, there's definitely touchier set theory in reals than the kind of set theory that I've involved you guys with.
Yeah.
I mean, I would say that's probably a deficiency of my course versus Dr. Sprano's. Like Dr. Sprano probably has more sort of fussy set theory stuff in his, and I tend to focus more on matrix stuff. But there's a wide intersection, of course, as well. But anyway, so here's number 37. Suppose that R is a ring with unity, and A is an element of R. So here we have R, a ring with 1 in the ring, and we also have A is an element of the ring. What else? Such that, I was like, that's pretty boring otherwise. So here's something interesting. A squared is equal to 1. All right. And he says let S, so this looks like a subring question, doesn't it? Ara. So he's like ARA such that R is in the ring. Prove that S is a subring of R. Does S contain 1? So basically, if you think about this problem here, A is given to be a unit. And I mean, from a sort of group theoretic perspective, we're just looking at the set of conjugates with respect to A, because A is A inverse. So, but anyway, that's kind of, I mean, whatever, but it's just going to be a subring test, all right? So let's see here. First of all, if we look at 0, A times 0 times A is equal to A times 0, which is equal to 0 by the theorem we went over yesterday. So therefore, 0 is an element of S, and we find S is non-empty. All right, we always have to check S is non-empty. Great. I would also point that S is clearly a subset. By inspection, essentially, S is a subset of R, right? I don't always say that, but technically we should say that. We do need it as a subset. And it's clear that it's a subset because it's formed from multiplication of things in the ring. So by the closure of multiplication. All right. So what we should do is we'll let R and S be elements of the subring. We shouldn't pick A and B here because A has a fixed but arbitrary meaning. So we can't pick A as an arbitrary element of the subring. That would be forbidden. And okay, so then we have, what do we have? Well, we have, oh, I'm an idiot. I can't do that. That's not what I'm sorry. I mean, that's not what I meant to do.
R and A, R, A.
Yeah, so there's two different ways to go here. So one way to write a little bit less and to be a little bit more to the point is, without loss of generality, we can let A, R, A, and A. Well, fine. Let me say it this way. Let R prime equal to ARA, and S prime equal to ASA be elements of the subring, right? So those are two arbitrary elements of the subring. And I'm just all right. Or if you want, you could say let S prime and R prime be elements of the subring. Because they're elements of the subring, there has to exist an R and an S for which S prime is equal to SA, ASA, and R prime is equal to ARA. I mean, that's what I'm saying with this statement. All right.
That's my question.
Yeah.
Closure multiplication sort of like an axiom, or like within a ring?
A ring is an additive group with respect to addition that also has a binary operation called multiplication.
Okay.
That means it's closed. But it's also associative, and it has the distributive laws. And it plays well with 0. But anyway, according to the theorem we proved. Okay, so here, if we look at R prime, S prime, we get, what do we get? We get Ara, Asa. Sorry, I'm an idiot. Right, so that's A, R, S, A. Right? Which is again an element of S. Because RS is an element, as element of the ring. So it fits the pattern to fit into the subring. Likewise, R prime minus S prime is ARA minus ASA, right? Now here I might have to, it's funny, I might have to think harder about the subtraction this time. Was this question to prove it was a subring, or was the question, is it a subring? No, prove it's a subring. And then we're also asked, does it contain 1?
And just use the left and right distributive properties?
Yeah, I think so. So I'll factor A out to the left here. So you're like, it's A times RA minus SA, right? That's by the 1 distributive property. I guess the right distributive property, right? I mean, correct. And then use the left distributive property there. Oh, yeah, and there you go. So using both of the distributive properties, that's an element of S, as R minus S is also an element of the ring, right? Because, again, the difference of elements in a ring is again in the ring. So consequently, S is a subring by the subring test. Does it have 1? Is 1 in there? There are 2 ways you could understand that question. When he says, is 1 an element of the subring? That's an ambiguous question in my view. Because like the example we looked at in class, the even z mod 6 integers, 1 was not an element of the subring. But 4, in some sense, was equal to 1. I mean, 4 was the unity of the subring.
So it could say, is the subring?
So yeah, there's 2 questions to ask here. Does the subring have a unity? Is that unity 1? The same as the 1 from R. My guess is that 1 is in there because he's asking the way he's asking the question.
A times 1 times A is just A squared.
Oh, A times 1 times A is equal to A squared. It's equal to 1. So therefore, 1 is an element of S. Yeah, there you go. Okay, very good. So ambiguity vanquished. It's just, 1 is not, the subring is unital, and it also has the same unity as it happens. Yeah. All right. The other question he wanted us to look at was, where was I? I'm trying to make sure I don't work one of your problems. Oh, I'm going to work a different problem here for a second. Number 31. He didn't request this one, but I like this one. Number 31. Give example of ring elements A and B with the property that AB is equal to 0, but BA is not equal to 0. Find ring with AB equals to 0, but BA not equal to 0. Obviously, this is not a commutative ring. So what should you think of when you're looking for examples for something like that? Do you guys have an idea?
Matrix.
What's that? Yeah, matrices. Exactly. That would be my go-to for this sort of thing. Matrices, or perhaps functions, like function compositions, not generally commutative. But I have an easier time visualizing matrices, right? Because I can just kind of like do something, try something out, you know, like, gee, I don't know, 1, 1, 1, 1, and 1 minus 1, 1 minus 1, that's equal to 0, right? Oh, that's not 0, sorry. I'll get it right eventually here. Minus 1, minus 1. Okay, so then 0, 0, 0, 0. This is also an example of zero divisors, right? For what it's worth. So I'm thinking of this as A and this is B. And let's see, on the other hand, what happens when I reverse the order? Is it still 0? It might still be 0. It might just, this might not work for us. I'm just trying. Oh, yeah, it works. Woohoo. 2, 0, 2. Oh. Why did I get 0? Not 0. It's minus 2, isn't it? As you can see, that's not equal to 0. Now, what ring am I working in? Yeah, we could do like Z2, the 2 by 2 integer matrices if you want. There's a fair number of matrix rings which have these in there. It's also true for like Z mod 3 with 2 by 2 Z mod 3 matrices, for example. You could fit this counter example to the, you know, well, you could fit this kind of example into tons of different matrix examples, is my point. Okay. The other, let's see here. Which one did I not put in your homework? 43. We could try. Well, I guess I'll do Blaine's question next here. Where was it? 47. Wanted us to look at this one. He says, let R be a ring all right, and here we have we're supposed to prove the following. Prove, we have the identity, a squared minus b squared is equal to a plus b times a minus b. What? For all a, b in the ring, if and only if what? Right. All right, so I'll do the easy direction this way. If AB is equal to BA, for all a, b, and r, then a plus b times a minus b is equal to a squared plus ba minus minus ab minus b squared, right? Which is equal to a squared plus ab minus b squared using commutativity, which is equal to a squared minus b squared, right? And that's true for all ab, right? So there's the converse direction. Let's see here what the forward direction. If I had, played my cards more carefully here, if a squared minus b squared is equal to a plus b times a minus b for all ab in the ring, what's that tell us? That implies that a squared minus b squared is equal to what? A squared plus ba minus ab minus b squared for all ab in the ring, right? Which implies what? 0 is is ba minus ab for all ab in the ring, right? And then of course that tells us that ab is equal to ba for all ab in the ring. So, that's Any other questions?
For one of the homework problems, we have to say the group of units.
How do you find the group of the units of the Gaussian integers? 23?
You have to prove that the Gaussian integers are a ring first.
No, I think
Or
that's...
else it's a ring, because it says an example when it says, we leave it to the student to confirm that each of the following examples is a ring.
Oh, well, I just want you to find the group of units there, really. We could prove that the Gaussian integers form a ring. It wouldn't be very hard. So to prove the Gaussian, so what are Gaussian integers? So that's the set of a plus bi such that a and b are integers, right? Formally, this is a subset of the complex numbers, right? So since it's a subset of the complex numbers, and the operations in the Gaussian integers are just that of ordinary addition and multiplication of complex numbers, we already know that the complex numbers form a ring. So I can use the Subring test, right? So notice that 0 is that element of zi, right? As 0 plus 0 times I is just equal to 0, right? So anyway, dumb comment, but here it is. Zi is not equal to the empty set. If you have a plus bi and x plus yi in the Gaussian integers, then you can calculate a plus bi times x plus yi, and that gives you one thing, and also a plus bi minus x plus yi, that gives you something else. Let's calculate. So we get ax minus by plus I times bx plus ay. Down here we get, it's easier, right? A minus x plus I times b minus y. But look at those. We're looking at complex linear combinations where the real and imaginary components are integers, because they're the sum and difference of integers, or product. sum of products, right? I mean, anyway, these, this, and this, all in the integers. So that means that this is an element of Zi. This is an element of Zi, right? Therefore, Zi is subring of the complex numbers. At the end of chapter 12, there's that beautiful subgroup lattice that he draws, right? He has all these different subrings of the complex numbers, right? So he's like, you got the complex numbers up here, then you got the reals there. Under the reals, you've got the rationals, right? Under the rationals, you've got integers. But the complexes, you can also go kind of sideways and look at the Gaussian integers, right? You can go from the reals, you can go over here, and over here you've got like q adjoin the square root of 2. We looked at that sum. That's in between the rationals and the reals. The Gaussian integers are between the integers and the complexes, you know? And then below z, you've got all these different stuff like 7z, and over here you got, like he says, 5z, and then below 5z you got 10z, right? Over here, 2z. 2z is above 10z. 2z is also above 4z, and he goes, you know, the list goes on and on according to divisibility, you know, and so forth and so on. And anyway, it's, as he says, it's a partial, right? Because you can go on and on and on and on. But anyway, so this Gaussian integer just fits into the story here. It's a number system that's between the integers and the complex numbers, whereas this is somewhere in between the rational numbers and the real numbers. You have one irrational number in this number system, so to speak. I mean, that's not quite true. There's lots of irrational numbers there, but there's like sort of one fundamental irrational number or two you're adding to the mix. Once you add that, then you can add it and subtract it and multiply it. And so it's sort of like a disease. It catches on and you get tons more irrationals just from having that presence of the one irrational there. Here's a problem I like. This shouldn't take us long to solve. Number 44 asks us to show that 2z union 3z is not a subring of z. So how would you go about doing that? I mean, zeros in there. Yeah, you need a counterexample. Definitely zeros in there, so that's not going to help us. I mean, when you're looking, one of the things I mentioned last class was like odd integers. Well, odd integers are not a subring because there's zeros not in there, so that's an easier one. But also, odd integers fail under addition, right? Like the sum of two odd integers is even, so it also fails to be closed under addition. What happens if you add two? Like, let's see here. In here, you have things like, well, you have 2, right? And you have 3. They're both elements of here, right? But what happens if you add them? Right? 2 plus 3 is 5. And that is not an element of 2z. And 5 is not an element of 3z, so it's not an element of the union either. Right? And that's just that theoretic union. It's not saying that you're adding them. Right? It would be a totally different thing if we asked, is 2z added together with 3z in terms of the usual addition of sets? Is that a subring? Yeah, probably that's a subring. But anyway, in fact, that's probably all integers. I'm pretty sure you can reach, well, yeah, look, the GCD of 2 and 3 is 1, which means that there exists 2j plus 3k equals to 1. So that means that 2jx plus 3kx is equal to x. For any x in the integers, you can reach any x in the integer in the sum of 2z and 3z. Totally different thing than the union.
So if we've done 3 minus 2 equals 1.
Say that again?
Another counter, 3 minus 2, which equals 1.
3 minus 2 equals 1 is not in there. Yeah, I mean, there are many. But when you're faced with a problem like this, if you want to convince me you know what you're doing, just give me a specific counterexample. Don't go on for 3 sentences about why it's wrong in ethereal, terms. Like, I need a specific concrete counterexample to be sure you know what you're talking about. Talking in vague generalities will not work there. So what I'll do with the remaining couple minutes we have in here is I'll just give you the rest of what I haven't talked about. Oh, no. Wrong one. Man, I got more notes to write today. It's endless, I guess. It's good, though. Writing these notes is what helps me be able to explain it to you guys. All right, so this was our lecture last Monday, and I added 2 pages to it last night. And really, I'm just finishing up chapter 13, right? Let's see here, let me get to it. These examples, what I did in class was I took the examples and I folded them into one big example. And the notes, they're ripped apart into 2 examples. Like, I first look at the ring and then I look at the group of units in the ring. So that's the difference. So anyway, here's a theorem that I don't think written on the board yet, but I think everybody will understand. Let A, B, and C belong to an integral domain, A not equal to 0, AB equals to, man, that's annoying, AB equal to AC, then B is equal to C. Cancellation. I'm not assuming that A inverse exists here. All right, so and the proof is shockingly simple. Check it out. So suppose you got a ring, not a ring, integral domain. An integral domain is a commutative ring with identity, right? All right, so, excuse me, does it have to have an identity?
Yeah.
Oh, it does, okay.
No, 0, 0.
More importantly, no zero divisors, right? Yeah, I'm burying the lead here. No zero divisors, right. So if AB is equal to AC, then you can rearrange that to AB minus AC equal to 0, factor out the A using distributivity. Then we've got A times B minus C equal to 0, right? So it must be that B minus C is 0 because we're assuming A is not 0. If B minus C was not 0 and A was not 0, that would be tantamount to B minus C being a zero divisor, which is not allowed because it's an integral domain. So there you go, bammo, cancellation. Even though A inverse doesn't have to exist, which is kind of cool, right? And so that has some pretty powerful applications. I mean, in the integers, you could look at 2 times x is equal to 6. Well, 6 is equal to 2 times 3. Therefore, x is equal to 3. That's not a very good example because you guys are still well, you just divided by 3. In your heart, you divided by 3, right? That's a little bit... Yeah, I know. But I get you guys a little bit further away from that way of thinking. If we look at polynomials with integer coefficients, that's an integral domain. All right. And so if I have x plus 3 times x squared plus 1 is x plus 3 times f of x, then I can conclude by this cancellation property that x squared plus 1 is f of x. Now all of a sudden I've said something that maybe is like a little bit more, oh, this cancellation property's got something to it, right? Now, spoiler alert, eventually we'll find out that you can take an integral domain and everything that's not a unit, you can find a larger space in which those non-zero things that aren't units become units. There's always something called the field of fractions over any integral domain. We'll construct that later. But for the moment, we're just doing cancellation. I've told you more than it's in the notes, but that's because you guys came today, so I'm being nice to you. Anyway, a commutative ring with unity for which every non-zero element is a unit is called a field. I did that last class. I mentioned that, right? So I'm just trying to... I'll ask the rest of the class just to read this. I'm telling you guys since you came. I guess I might tell them I talked about it here. I don't know. But I'm worried about doing that because then they're going to accuse me of making them come to class 5 days a week. I don't know. There's no telling what they'll do. Let's see here. Oh, check this out. Each finite integral domain is a field. Say what? Each finite integral domain is a field. So if you have an integral domain that doesn't have infinitely many elements, it's a field. Counterexample, or it's not exactly a counterexample, but side example, integers. That's an infinite integral domain, which is not a field. You might wonder, is there some kind of like z mod something? Well, you kind of know z mod something is out, because you know that z mod n is only a field when every non-zero element is a unit, right? But that's exactly when n is equal to a prime, because only when you have a prime do you get the up is just everything except for 0, right? If n is composite, then the product of those things making up the composite form of n, those are zero divisors, right? Like 6, 2 times 3, well 2 and 3 are zero divisors, or 10, 2 times 5 is 10. 2 and 5 are not 0, but 2 times 5 is 0, 2 and 5 are zero divisors. You go on and on. Any composite n, the numbers making up the composition of n as a composite factorization, those will be zero divisors. Only in the case that n is prime do you get no interesting, you only get 1 times p, or p times 1, or minus p times 1. But anyway, but those are just 0. So 0 times 0 doesn't move. 1 times, well, anyway, I'll shut up. So here's the argument. D is a finite integral domain with unity. Pick a point, A and D, with A not 0. If A is equal to 1, then it's its own inverse. Great. Otherwise, A is not equal to 1. So you can look at the list A squared, A cubed, and so forth and so on. But D is finite, right? So eventually this list of powers of A has to come back to somewhere. Now, I shouldn't assume it comes back to the start of the list. Who knows where it comes back? But it's got to loop back eventually. Otherwise, the list would go on and it would be infinite set. So that's impossible. So without loss of generality, we can assume that there's two, like AI is equal to AJ for some I and J. And we can assume, I think I assume basically that I is greater than J. We can do that without loss of generality as well, right? I mean, one's got to be bigger than the other. But anyway, A sub I equals to A sub J. So that gives you, by the usual exponent notation, A to the I minus J is equal to 1, which then gives you AI minus J minus 1 times A equal to 1, which means A inverse is this guy. Every non-zero element has an inverse because A was arbitrary. I mean, if that doesn't exhaust the list, you go on to the next. I mean, I just picked an arbitrary A, though, so I found an inverse for an arbitrary A. So, yeah, that's actually it. And there you go. That's a field, because everything that's non-zero has an inverse. This argument, to me, is one of those arguments that I kind of remember from the first time I studied abstract algebra. And even there, when I first saw this argument, I was like, whoa, that's like too easy. I hope he puts this on the test. Like, I understand this one. Yes! Anyway, if P is prime, Z mod P is a field. And so the proof is here. So if you have AB equal to 0, that means A is equal to PK for some multiple of P, K, right? But by Euclid's lemma, if you've got this, if you've got a prime times that, that means that the prime either has to divide A or has to divide B, which means either A or B is 0 in ZP. So I usually would just claim this sort of thing is something we already know. I'm just giving added detail here for the sake of anybody who's in doubt. Here's Z3. This might help you. I was going to talk to you, like, how do you find the group of units in the Gaussian integers? Do you guys think about it? It's just an algebra problem. I mean, and I mean that in the...
A plus bi times c plus bi equals 1.
Exactly. You want to look for solutions to a plus bi times c plus di equals to 1. That should allow you. And if you think about it, since it's a subring of the complex numbers, you can use complex number manipulation to find it. Or you can look at it as a problem of like, fix the a and the b, then the x and the y are like variables. And you can look at it as a system of equations, an x and y with the matrix, which is made of the a and b's. And you'll be able to solve that system using linear, basic like 2x2 linear algebra, I think. Kind of like this. So here, this is actually the same thing, but for zero divisors. I'm looking for possible zero divisors, right? So you would put a 1 here, I put a 0 here. But it's kind of the same song and dance, except that my x and y are taken from z mod 3, whereas your x and y will be integers in the Gaussian integer problem. But otherwise, it's kind of the same animal. Man, that's annoying. Anyway, you take these two equations and you can regroup them like so. It's no accident that this is the matrix representation of a complex number, x plus iy. But anyway, just saying. Anyway, so this multiplied by the inverse both sides, then these cancel because, by the way, x squared plus y squared is non-zero for every one of these guys that's non-zero. Like 0 squared plus 0 squared is 0, but all the other ones, x squared plus y squared either works out to 1, 4, 1, 2, 5, 4, 5, 8, I think. Anyway, so that gives you that AB is 0. So consequently, if you have the product of two things in here being 0, you're forced to have one of them be 0. So there are no zero divisors. This proves, in fact, that Z3 with I adjoined, this guy, is an integral domain. These details are not in Gaussian, I added them. I'm trying to be nice to you guys. This is a very significant help for 23. The other example, this is Q adjoin square root of 2. And here's the proof that it's an integral domain. Multiply them, get something in the same form. If you want to look at what are the units, this actually proves it's a field, because if you look at, try to find, I'm trying to find that equal to 1. It's really cool. Look, it's just the same as the formula for complex, except instead of multiplying, you multiply by the conjugate over the conjugate, but here the conjugate is changing root 2 to minus root 2. But still you get something like this. And by the way, a squared minus 2b squared is not 0 for a and b being rational. That's a math 200 factoid for you. I haven't really proved that in here, but it's true. And so that's again something in Q adjoin root 2, which shows you every non-zero element has a unit, which basically you just get from the reciprocation of a real number. That's all that's really going on here. But anyway, this is a field which is between the rational numbers and the real numbers. And then here's the characteristic, and we talked about that last class. Here's the proof that you can just look at 1, and here's a proof that the characteristic of an integral domain is either 0 or a prime. And I'll let you look at those. I think I've talked enough in here for today, so I'll shut up. But unless you guys have questions. It's not bad. There are something here, I haven't really, there's a couple homework problems in Gaussian about proving that this dot notation is legitimate. I almost assigned you guys one of those, but I think they're kind of tedious and boring. And I'm trying to get you guys to focus more on the meat and potatoes of the section, which is subring test, subring test, subring test, subring test. Get examples of rings, examples of rings, examples of rings, and, you know, learn how to show something's not a ring. So that's why as much as I am drawn from my foundationalist side of me to assign you guys number 14 and 15 and 16 from this section, I have resisted the urge to do so. But admittedly, that's a gap in our, you know, development. So I'll shut up. Well, I'll shut up in a second here. I'm going to turn off the video. I would tell our cameraman to turn it off, but, well, I am right now, but.